Let's do the following. First, let's choose 2 points and label them AFA and BFB. Any 2 points that you just like. Now I'm going to choose a point on the y-axis that is between f of a and f of b. This is what I choose. You can choose any one that you like. Now we are going to draw a horizontal line through this point. Here's the horizontal line. And now it's the tricky part. Let's try to sketch a graph of the function fx such that fx is continuous on AB and fx does not cross the orange line that passes through the point that I choose between fa and fb. Let's try. Doesn't work. Doesn't work. Doesn't work. This is definitely impossible because I need to reach from the point AFA to BFB, and I need to go only from left to right because this is a function. It means that I cannot go back. And the question is, why? Is it impossible? Because there is a theorem that says the following. The intermediate value theorem, in short IVT. Let fx be a continuous function on the closed interval AB. Then fx must take all values between fa and fb, which means that at some point we should have crossed the line. Here's one point, AFA as before, and here is BFB as before. And here are all the values between FA and FB. And if you can see, this function that was just arbitrary continuous function really attained all the values between FA and FB. If you don't believe me, let's check. Every time that a function gets a value between FA and FB, it's going to cross this line. Yep, this is true. Of course it is true, because if you look at the graph of the function, this is a continuous function on the interval AB, and there is a theorem that says so. For example, now when we take n to be between f of a and f of b, then there is at least one value x equals c between a and b, such that f of c equals n. Here is the n. It's a y value that is between fa and fb. And as you can see, it crosses the graph at this point. The x-coordinate of this point is c. And as you can see, c is between a and b. Here is then the precise intermediate value theorem. Let fx be a continuous function on the closed interval AB, and let n be a number between fa and fb. Then there is at least one value c in AB such that f of c equals n. Theorem. Here is a special case of the intermediate value theorem. If fx is a continuous function and it changes sign on the closed interval AB, then it has at least one zero on the interval AB. Let's take an example. Here's the point AFA, and now I'm taking the point BFB, and as you can see, the function is positive at FA and it's negative at FB. By the intermediate value theorem, because the function is continuous on the interval AB, it must cross all the values between f of a, f of b. Now we take a very specific value. The value between f of a and fb in this case, is the y value when y equals 0. Because the function changes sign, y equals 0 is always between fa and fb. It means that the graph has to cross the x-axis. It means there is some value c of x for which f of c is 0. Be very careful. The theorem does not tell us what are the zeros. Also, the theorem does not tell us how many zeros there are. It only says that there is at least one zero. Example. Show that the function x cubed minus x to the power of 2 minus 1 has at least one zero. We will apply the theorem. First, we have to notice that the function is continuous because it's a polynomial. Now we have to show that f(x) changes sign on the interval 0, 2. Because f of 0 is negative 1 and f of 2 is 3, which means it is negative at f0 and positive at f2. So applying the theorem, we get that f(x) has at least one zero on the interval 0, 2. Example. Show that the equation x cubed equals x to the power of 2 plus 1 has at least one solution. We are going to do a trick. If x cubed equals x to the power of 2 plus 1, it implies that x cubed minus x to the power of 2 minus 1 equals 0. So I have to show that the function x cubed minus x to the power of 2 minus 1 has at least one zero. But I did! And because I did, I can conclude that there is one solution for the equation x cubed equals x to the power of 2 plus 1. Be careful. We cannot find the zeros. We just conclude that there is at least one, maybe more, zero. Example. Assume that a continuous function g of x gets the following values, and here is a list of values for the function g. How many zeros does the function gx have on the interval negative 3, 2? First, we notice that the function is continuous, so we can apply the intermediate value theorem and also the theorem that is resulted by the intermediate value theorem. So here is the list of the values of g. I'm going to highlight in blue all the positive values and in yellow the negative values. Now we just have to notice how many times the function is changing the sign. There is one change in the sign here. By the theorem, we know that the function has at least one zero on the interval negative 2, negative 1. Here is another change in the sign of the function. So there is at least one zero on the interval negative 1 and 0. Here there is another change in the sign. So there must be at least one zero on the interval 1, 2. We can conclude then that g has at least 3 zeros. Pay attention. It may be more, but g has at least 3 zeros.